Hey everyone, welcome to a short video lecture on continuity. This is Nicholas JMV. So let's go ahead and get started with this idea of continuity. Okay, so in precalculus, we're going to be talking about a really informal definition of continuity. Okay, so the idea here is that a function is said to be continuous if you can draw the function and never lift up your pen or pencil. Now that's a very basic definition, and that's all we're using for now in precalculus. As we get further along in our discussion, we're going to learn what continuity is and what you need to pass algebraically in order to be continuous. But the idea here is if I have my pen and I want to draw this nice little function here, and it can be anything. I can come up, so I'm just drawing some function, okay, and we're going to call that f of x. So I drew that whole thing without lifting up my pen, and notice there's no gaps, jumps, holes, or anything. That is a continuous function. So if you can do that right now, that is the idea of a continuous function. Okay, in this video lecture, all we're really going to be talking about is types of discontinuity, and the first one we're going to talk about is a type of removable discontinuity. A graph is continuous everywhere except for the hole at a point at x equals a. So if I draw this point, here's this point A, I don't know what it is, okay, and I can go ahead and draw up, and maybe there's a hole here, and my graph continues on like this. So what that means is there's a hole in my graph, and I can't draw the complete thing. That means all these points are defined for y except for this value here at a, and then this would be f of a. So that point is not defined. There's a hole there. This type of discontinuity usually happens when you factor. When we start factoring and taking out discontinuities, you'll see this type of graph. So that means there's a hole. This is what we call removable, okay? Because it actually, essentially, instead of having an asymptote here, you remove the discontinuity. So that's one type. The other one that looks so familiar to this is point discontinuity. And so the graph, it's a graph is continuous everywhere except at x equals a, the same as the removable discontinuity. However, f of a is defined at another value. So if I have, this value at a again, and I go ahead and draw my graph, and I have this hole here like I did last time, it's removable. The only thing different here is that at a, this point's undefined. It means that somewhere else along that graph, we have a defined point there for f of a. Okay, at a, when we plug in a to our function, we have a value down here. That's the big difference. So that's also a removable discontinuity, but they call that point discontinuity. Okay, so it's very similar to the other one. Oops. Okay, now this one is called jump discontinuity. Now this is not removable. Jump discontinuity, this discontinuity is not removable because there's a jump or a gap in the graph. A lot of piecewise functions can be great examples of this. For example, if I have a piece of my function going like this, maybe it's a parabola here, okay, and then down here it jumps an open circle. Maybe I have a line going this way. And what they're talking about, the jump, is that in order for me to draw this graph, I have to go here, stop, jump, and continue on my graph. So there's too big of a gap here. Okay, so that's what we call a jump discontinuity. Pretty easy to see because you have to jump to finish your graph. Okay, and lastly, the infinite discontinuity. Okay, and I have to draw that in. Infinite discontinuity is also not removable, just like jump discontinuity is. It will be for functions containing asymptotes. And a good model of this is rational functions. Say we have like one, okay? Say we have a function looking like this, okay? And we have removable discontinuities here. You can draw the graph here, but then we have to move down here to draw f of x. So we have another discontinuity, and it's infinite because there's an asymptote here. There's a vertical asymptote at x equals 0, but that's called an infinite discontinuity. So those are types of discontinuities we look at. Okay, those are the 4 types. An example here, if we looked at, graph the function and tell whether or not this has point discontinuity, okay? And so we can go ahead, if the discontinuity is removable also. So graph the function, tell whether it's point discontinuity at x equals 0. If it does, the function, state the type of discontinuity if it's removable or not. So if I was looking at h of x, okay, I would simply say h of x is equal to x cubed. Now there's only one term in the denominator, so let's use some algebra here. And we'll split this up, x cubed over x plus x over x. Okay, now I can graph this function, okay, and I have x squared plus 1. Okay, that is a parabola. Okay, so I used some algebra here and I simplified that if I was going to toss the graph on here. Okay, this is a general sketch of the graph, doesn't have to be perfect. At 1, we have x squared plus 1, excuse me. Okay, so that is a continuous function. That's continuous everywhere. It's a parabola. It's a polynomial. Okay, polynomials are continuous everywhere. So this doesn't have any discontinuity. There's a polynomial after I simplified. Okay, so that's our first graph. Let's look at our second graph, 3 over x. Okay, now I can look at that and say, well, mathematically, I know x can't be 0. Okay, that would make that undefined, 3 over 0. So if I graph this, okay, it's going to be 0 I can't use. If I use 1, I get 3. 1, 2, 3. Okay, if I get 1, I get 3. If I get 3, if I plug in 3 for x, I get 1. And if I use negatives, if I use negative 1, I get negative 3, okay, for my graph. And if I plug in negative 3, I get negative 1. So I can go ahead and draw my graph in. Now, this has discontinuity. Okay, so graph the function, tell whether or not it has point discontinuity at x equals 0. Well, it doesn't have point. It has infinite discontinuity. Okay, so if it does have discontinuity, is it removable? This is non-removable. So that's the type of problem you're going to go ahead and see in your homework. Okay, so if you have any questions or comments, let me know, everybody. Thanks for your time. We'll see you next time.